Okay, so for this topic, we will be discussing external force convection. No? So there are three types of external force convection that will be discussed. The first one will be over a flat plate. The second one is flow across cylinders, and then flow across spheres. Actually, there is also a fourth one, which is across tube banks, which is basically just a collection of cylinders, no? But anyways, we won't be delving into that too much, but I will be still giving out notes for tube banks. No, still it is quite essential, but not really that essential that it will be a problem moving on within this within studying heat transfer. Uh, So this fourth scheme of external force convection obeys a similar process, similar to this over a flat plate and cylinders and spheres, but it won't be part of our assessment as well. So let's first define what is external force convection. No? So in external force convection, the fluid is moving across this body. No, so outside, no, external of this body. So heat transfers through this fluid and this body. So for this first example, you have an airplane. So if you imagine airplanes go at a very high speed, no, and there will be some heat loss, no, assuming that the cabin, the airplane is hotter than the surroundings, it will reject heat, no? And this heat rejection should be known because it might be important for the thermal stress, no, or the material for the material integrity of this airplane. Also, it might be important for air conditioning and so on. So that will be important for the second example for let's say a house. So we experience this gradual wind blow and it might affect our air conditioners, no, or the heat that is be experienced by the inhabitants of this home. So we want to, I mean, in general, convection really involves two things, no, fluid mechanics and heat transfer, and it is actually quite complicated, no, to describe. And usually, we only have some statistical or empirical relationships to help us simplify this phenomena. And the previous topic that we've discussed, wherein we've discussed the different dimensionless numbers such as the Nusselt number and Prandtl and Reynolds number, it will be important for these simplified equations to solve for problems in convection. So let's start with the local Nusselt number. So for the local Nusselt number, you have this. In general, you have a function of this Nusselt number with relationship with the Reynolds number at this specific point and the Prandtl number. So the x star here is the usually just a ratio of or a non-dimensionless, no, number that represents the position of this point, no. So when you say local, it is at some point, no, it is only at some point applicable. But if you say the average, no, you find this all these local points, no, in this for example a plate, you can find the average, no, of this whole. So we are usually only interested, no, for this engineering subject, the average Nusselt number. So the general form of this relationship of this Reynolds number, Prandtl number, and the Nusselt number is in this form. So you have a constant times the Reynolds number raised to m and the Prandtl number raised to n. So remember that there's no side note here that the properties should be evaluated at the film temperature, which is the different sorry the average also, no, temperature of the surface and the free, no, free stream temperature. Okay, so in external force convection and even in internal force convection, it will be important to know whether the flow scheme is laminar or turbulent. And the way to describe if the flow is laminar or turbulent, is the Reynolds number. So if the Reynolds number is within, no, this limit, then it should be fully laminar. But if it exceeds this number, it might be partially turbulent or even completely turbulent, or a majority is turbulent. So for parallel flow over a flat plate, our first scheme, no, it will be um if it will be 500,000, no. So if it reaches 500,000, the flow will be turbulent. If it is lower than that, then the flow over this flat plate is laminar. So X here is this horizontal position of your plate, no? Or where are you measuring, wherever you are measuring. Okay, now we know that some cases it will be applicable laminar or turbulent. Now we want to define, how do we find the Nusselt number? So take note, why do we need to know the Nusselt number? We need to know the Nusselt number because we can find the H, no, the convection transfer coefficient using this Nusselt number. Okay, so for local, no, so local Nusselt number across this plate. Before we start, no, there's a difference between local and average, no? So we will just briefly discuss the local version. So the local Nusselt number can vary, no, within its local point, no? So if it is local, ibig sabihin yan, the Nusselt number could be high at this point, no, this point. The Nusselt, sorry, yes, the Nusselt number, no, Nusselt number could be low at this point, no, for example. But we're talking about nga pala the H, no? So in this case, this is the graph of the H. But the Nusselt number could be lower at this point or anywhere, no? So it changes depending on the X. So we have an X here, meaning it is dependent upon the position, this local Nusselt number. But we are not really that interested with local Nusselt number. We want to find the macro, no, version. So we want to just find the average, no, the average representation. So if you find the average of this, which is actually an integral, so if you find the sum, divide this by the total number of points, that's the average. So basically an integral divided by the length, no, which in this case is this. If you simplify this Nusselt number with relation to each, then you will have a value here, no? So it will have this average Nusselt number for laminar and for turbulent flow. So depending on the scheme, you can find the Nusselt number for laminar. So the fully laminar is when the Reynolds number at full length is less than 500,000. This will be the relationship to find H. For fully turbulent, you have this relationship. No? So if it is greater than 500,000, it will be, assuming that along the length, no, starting from, let's say here is 0, along this line, it will be fully turbulent. This will be the relation. But frequently, will only need to use this too for most of the part, no, since most of the schemes in external flow is either fully laminar or mixed, no, frequently, no, for these examples only. But anyways, there could be a case anyways that it could be fully turbulent. So if it is partially turbulent, so for example, the length is about this, so there is some turbulence here introduced. So don't be confused of transition region, no. We can assume that transition region is also turbulent since it is already partially turbulent. But again, no, transition is the overlap of the laminar and the turbulent part, no? So it is kind of getting into turbulent, but it is a little bit laminar. Okay, so usually we will use these two equations. So they have different formulas, no? But you will get onto it soon, no? So they have similar limits for fully turbulent and for mixed. Okay, now we can have an example for this next slide. So I'll just record this in the next video.